Okay, so where we ran out of time on the last video was doing an example to figure out what's the gravitational force of attraction between two of you who are 2 meters apart. So the constant, 6.673 to the negative 11 Newton meters squared per kilogram squared. And don't worry, after 5 more minutes, you won't have to know this constant. You'll see it again when we get to grade 12, okay? 60 kilograms, 80 kilograms, and then you divide it by r squared, which in this case is 2 meters squared. Okay, so maybe pause the video for a second and type that in. And I had it typed in and I just cleared it. 6.673 to the negative 11 times 60 times 80 divided by 4. Okay, and what you should get, if you can do scientific notation in your calculator correctly, is 8.0076 times 10 to the negative 8. Then kilograms and kilograms cancel out the kilograms squared. Meters squared go. We're left with newtons. So the force, the gravitational force of attraction between two of you who were 2 meters apart is 8 to the negative 8. This is minuscule. This is so tiny that we would not be able to notice it. We do not perceive it on a daily basis. It is there, but we can't feel it. And if it's that tiny for two people who are 2 meters apart, then imagine how tiny it is for you and I who are across the city from each other, or you and someone in England. You're putting a force on them, but it's going to be so small that we can't feel it. So now let's trade one of you in, and let's keep the 60 kilogram person, and let's trade in the 80 kilogram person, and let's use the mass of the Earth instead. The mass of the Earth is 5.98 times 10 to the 24th kilograms, and I know that because of the planets unit in grade 12 physics. And the radius of the Earth is 6.38 times 10 to the 6th meters. So we'll keep the 60 kilogram person, and instead of the 80 kilogram person, we'll use the Earth. And let's find what is the force between the 60 kilogram person and the Earth then. So 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared times 60 kilograms times 5.98 times 10 to the 24th kilograms, significantly heavier than you and I, divided by 6.38 times 10 to the 6th meters squared. Okay? So take a second and punch this in your calculator and see what you get. You can pause the video while you're doing that. Okay, so if you punched it in correctly, you should get 588.21 newtons. Significantly bigger than between the two of you. This is big enough that we can feel it. This is big enough to actually move us. That's why if I step off my bed, straight out, the Earth pulls me down. This is a large enough force that I will actually be moved by it. Now, the Earth won't be moved by it because the Earth's mass is a lot bigger than mine. Because my mass is tiny, this force will move me. Now, we could do exactly the same thing, and we could find what is the gravitational force of attraction between the 80 kilogram person and the Earth. So we would just take the 60 out and put the 80 in. And then we could do it for everybody in the class. So remember, back in the 1600s, when Newton was coming up with this equation, they didn't have calculators. So if they wanted to figure out this force for everybody, they were like, okay, listen, man, you're killing us. Because the only thing that's changing is this 60 kilograms. But this first constant and the radius of the Earth and the mass of the Earth isn't changing. So wouldn't it be easier if instead of using all of this, if we change this into one constant instead of these 3 constants? And that way, without a calculator, we wouldn't be dying here all the time. So pause the video again and find out what this is equal to. This 6.673 to the negative 11 times the 5.98 to the 24th and the 6.38 to the 6th squared. Find out what that will give you when you multiply them and divide them together, okay? I'll wait for you. Actually, I'm going to do it too. 3 to the 11th times 5.98 to the 24th divided by 6.38 to the 6th squared. And I didn't say it, but like you might not be right on the surface of the earth. You might be, if we were in class, we'd be on the second floor of Leo Hayes, which would be maybe 10 meters up. But you can add 10 meters to 6,380,000 meters and it's not going to change this number at all. Okay? When you do this, you should get 9.803495, etc. And if you look at the units, they will be meters per second squared. This is, if we had totally accurate numbers for the mass of the Earth, because it's not 5.98 with 22 zeros, and the exact radius of the Earth, we would get 9.81. This is the acceleration due to gravity, which, because it's a special acceleration, when we're talking about forces, we call it little g. Okay, and so this equation, gmm over r squared, gets simplified to Fg equals mg, which is what we will use for this whole course. We only use the big guy if we're not at or near the surface of the Earth. So as long as we're at or near the surface of the Earth, this little g is going to be 9.81 meters per second squared. If we're at the top of Mount Everest, if we're in the International Space Station, then the r changes. And if this, so it won't be 6.38 times 10 to the 6th anymore, and then that'll change the little g. If we're on the moon, if we're on Mars, if we're on Jupiter, both the r and the mass will change. And so little g won't be 9.81 anymore. But we can always find its value. It just won't be the same as what it is when we're at or near the surface of the Earth. So as long as we're at or near the surface of the Earth, we will use Fg equals mg, or as long as we know the little g of wherever we are. This guy is the universal law of gravitation, no matter where you are in the universe, because big G doesn't change. This one is dependent on the little g. So in your textbook, on page 132 and 133, there are two charts. The bottom of 132, there is a chart that shows you, that shows you what the little g's are for different spots on the Earth, the North Pole, the equator, Mount Everest, because the height is different. It's not quite the surface of the Earth. And so for the suggested problems this evening, you will need that chart. And on the facing page, there is a little chart for what it is on the Earth, the Moon, Mars, and Jupiter. So as you do your suggested questions for this evening, these two charts will come in handy. So they're on 132 and 133, okay? And so the questions that I would like you to do, let me find where I'm writing here, page 137, numbers 1 to 4. Okay, and the charts are on page 132 and 133. But the was, I almost forgot this blank. What is the other name for the gravitational force of attraction? The other name is, it's the object's weight. The force that the Earth is pulling on you is the object's weight, and we can find it as long as by Fg equals mg. Back when I was giving you the definitions of weight and mass, I said mass doesn't change no matter where you are, but weight does. And the reason weight does is because little g will change depending on if you're at or near the surface of the Earth or on the top of Mount Everest. Okay? So if it tells you an object's weight, it's telling you Fg. All right.